And I have no idea what this is supposed to be, but let's try it out. It should probably be a rather big number. Look at this. It's so beautiful. 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 Sup guys, welcome to today's show. So let's create a key schedule, shall we? In the last episode we finished the f function, which in turn is equal to the 3 atomic operations, which is the expansion, the substitution, and the compression. So the next thing is creating a key schedule. So we're going to go in with KE, which is a 128-bit encryption key. The output is K0, K1, K2, all the way up to K15, also at 128 bits. And these are the subkeys that will be used for the actual encryption. And K0 is going to be the same as the encryption key. And these other ones are going to be slightly modified. So basically, each round we are going to rotate left of the input 7-bit positions. Then we're going to push it through the G function, which is going to take the first 12 bits and put it through the S-box function that we already have. So we do the substitution, and before we do that, we are going to add a RC, a round constant. So we have already created a couple of RCs, so RC0, RC1, etc. Each of them are currently 64, but I'm going to change it to 16 bits. And then I'm going to create a prepare function, or maybe I'll just call it P, which is going to take RC0, for instance, and take RC0 appended to RC0 4 times like this, turning it into a 64-bit round constant. And then we're simply going to take the key 0 and times it with RC0. And this is going to be a 2 to the 128-bit modulus. Then we put the first 12 bits. Actually, it's the 12 MSBs, most significant bits, through the S-box, not affecting the rest of the bits. And all this is one round. And each round produces one of these keys, so it'll be 15 rounds. Or KE will be copied to K0, and then we'll do it 14 more times. That's how it's done. Okay, so you might not understand all of this now, but it will be much clearer when we write the code for it. So we already have some functions which relates to the keys. So we have this empty we have the empty make subkey. So this is where we're going to do the magic. We already have a make round key, which just creates this round key structure, which looks like this. So we have an ID 0 to 15. We have a subkey, which we are going to generate. we have the round constant, which is going to be int 16 instead. And inside of the constants, we have all of these round constants here. So let's see, we need to change this make round key so it takes an int 16 instead of 64. Maybe we can do it like this. So this will remain int 16, but we can store the prepared round constant instead. So we don't have to run that function multiple times unnecessarily. So let's take a look how the make round key and the generate subkeys functions look currently. So make round key. So all we're doing right now is we produce this basically empty structure. And make subkey is just returning the input as of now. And the generate subkeys is creating 15 of these. So instead of just saying RCs of X, we're going to push it through our prepare function, so the P function, like this. So the make round key is going to take, okay, it's going to take a 64 here. But these will still be in 16s, so we don't waste memory unnecessarily. Sup guys, welcome to today's show. So today we're going to discuss the key schedule of the XSC cipher. So we're going to have an input, which is a 128-bit encryption key, which I'm going to call KE, encryption key. So that's the input. The output is 16 subkeys. So K0 to K15, also 128 bits. And then in addition to this, we are also going to have 16 round constants, which are based on the Fibonacci numbers. So 1, 1, 2, 3, 5, 8, 13, and so on. The 16 first Fibonacci numbers. All right. So the key schedule looks as the following. K0 is equal to the encryption key itself. And that's our input to the function. So we are having the K up here, 128 bits. And what we are going to do is first we do a rotation. So we rotate the whole thing to the left 7-bit positions. That's step number 1. Step number 2 is we take the output, which is also 128, and we put it through the G function. And as input to the G function, we also provide RC0 in this case. And this is a 16-bit round constant. And out we get 128 bits still, and this is K1. And then we take K1 and we feed it back into the rotation and the G function. And we do this 15 times. So we have K0 all the way to K15. Okay? So what's left is defining what is the G function. So into the G function, we go in with a key. Of 128. And the first thing we do is we prepare the first round constant. So this is a function which takes the round constant of 16 bits and it provides a 64-bit output. And the prepare function is very simple. So prepare of x is just x, 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 x. And this pipe symbol here, that is an append. So basically we just repeat the 16-bit round constant 4 times and put it next to each other. And how do we do this in C? Well, we take the x, shift it 16-bit positions, and we OR it with x. And then we repeat this 3 more times. So now we have a 64-bit round constant. And we take the key, alright, so we take the round constant, we take the current state, current key, and we do a multiplication. And what kind of multiplication is this? Well, it's a regular multiplication. So let's say we have RC prime, let's call it, which is equal to the prepare function of RC0 in this case. So that's this. And the K is going to be equal to the RC prime times K mod 2 to the 128. So it's a 128-bit regular multiplication. So that means we get a 128-bit value out, but we're going to chop it off. So we're going to have a, let's call it, let's say we have K prime here, which is the first 12 bits of K. And here we have the rest. Let's call this K double prime. And this is the rest of the 128, so 116 bits. And this we push right through, but this, as you can imagine, we push through the S box. And then we're back at 128. So the only thing we do here is we chop off the first 12 bits, we push it through the S box, replacing it, and we put it back together again. So this right here is just K prime appended to K double prime. And this is the output of the F function. So how can we describe this G function in a more structured, mathematical kind of way? Well, let's say we'd first create the RC prime, which is the prepare function of RC0 in this case. Depending on the round, it might of course be any other RC. And let's see here. So K1 is equal to the G function of the rotation 7 bits left of K0, like so. So we rotate K0 7-bit positions to the left, and we push it through the G function. And G of X, let's say, is equal to the RC prime times X mod 2 to the 128. And then we do the, let's see how we should write this. I think I need a bit more space. So we take this right here. And the first, let's see, how do we usually write this? Colon. No. $11 0. So that means the first 12 bits. No, we can't do this without an intermediate variable. So let's create one. Let's say we have a k1 prime. And this is equal to the RC prime times k1 mod 2 to the 128. And then we divide it up. So we have a k prime which is equal to k1 prime bit number 0 to 11. And we have a k double prime which is equal to k1 prime. And this is bit 12 to 127. And then we have k1, which is equal to the S box of k1 prime appended to k prime, and this is k double prime. Okay, maybe it was easier to understand in the graphical view, but this is the mathematical view. So we prepare the RC0, the round constant, which is just taking it 4 times, appending it to each other. K1 is equal to the g function of the rotated k0, and we rotate to the left 7-bit positions. Then we multiply the round constant with k1 mod 2 to the 128, so a 128-bit multiplication. And then we just chop it off, so we take the 12 first bits, push it through the S function, and append it to the rest. So this is the whole G function. Or this is the whole round, actually. And then we do the same with K2, K3, all the way up to K15. So now I believe we have all the individual pieces for the XSC256. There are some extra stuff in the Penguin version, but I think I'm going to wait with that. So let's write the code for this instead. See you just in a bit. Alright, so where were we? We were going to create this P function which will prepare the int16 to become an int64. So it's quite a simple function. So it is going to return an int64. It's called P for prepare, and we have an int16 input. So what we are going to do is define an int64. Let's do, let's call this y, and let's have an int16 maybe it's enough with just a y. So we set the y equal to 0 to begin with. Now we're gonna need at least another int 16x, where x is equal to it's equal to the input, or we can set it to 0 ORed with the input. So we show our intent, or maybe not. Okay, so y is going to be equal to, and we take the x and we push it 16, 32, 48 bits to the left. Maybe it's easier to, let's see here. Well, let's do this first. And then y is equal to the current value of y, ORed with x shifted 32. And then we do the same, only this time we just shift it once. And finally, we just do this. And we can actually do like this instead. It's the same thing. And then we can remove this part. Something like this. And then we return y. Okay, so let's create a show function for 16 bits. So show, and that's quite easy. So show int 64. We do the same construction with an identifier and then an input. And at this point we can do it in one go. So let's see here. We need, for a 64-bit integer, we need 16 hexadecimal digits. And I think this will be LLX. And this will be an long int, I guess, input. So something like this. And now we only, maybe we can return as well. And now we can add this to our list of show functions. So we're gonna have an int64 show int64 like so. And let's test it out. So let's say we have an int16x and int64y, and we set x equal to let's say AA, BB, CC, DD, y equal to the P of x, wait a minute, it's supposed to be a 16-bit thing, so only AABB then. And then we show y and we return, and let's say we have a regular int main function which just returns main2 in this case. Right, something like this. Let's see if it compiles. Left shift count width of type. Okay, we need some casts. So let's put back these parentheses. And then we cast this to an 8-bit integer. I don't think we need it here. Okay, let's try it again. Maybe we should not have the parentheses. Okay, that's better. 41, I forgot the identifier. Called object P is not a function or function pointer. Okay, I called, that's bad. I quite often call pointers P. Let's say this is capital P instead. So we don't have to change a whole lot of variables. $217. Right, this is not supposed to be int. Let's update these as well. Alright, it compiled. And it looks like it works. It repeats this thing over the whole thing. Exactly as we wanted. Alright, good. So what's next? We need to define the G function. So we're going to go in with 128 and return 128. And this is the G function. We're going to have an int 128 here as well. And we need to create the rotations. And if you don't know what a bit rotation is, if we have, let's say, these 4 bits, and we want to rotate this 1 bit to the right, let's say, that means that we shift everything 1 step. This 1 right here will fall off the edge, and we're going to put it on the left side instead. So that's what we want. We want to have one function or macro which does this, and same in the other direction. And then we can create a function which repeats this if we want to do it several times, which we do. Alright, so let's see. I think it's easier to create a macro for the 1 step shift. So let's say we define let's call this we can call it rotate left 1. And we need to provide how many bits the integer in question is. So let's say this is number of bits, and this is the input. So let's see here. We want to take the input x and we shift it 1 bit position. So let's see if we have this right here and the output on the line below. So we shift this 1 step, like this. So this 1 here will fall off the edge. This will automatically be replaced with a 0. So this is what we currently have. Now we need to OR this with a bit that disappeared. So we're gonna OR this, and then we need to grab the first thing. So we need to do an AND operation that looks like this. So we select the first bit. And this is, let's see here. So if we have 4 bits like this, and we start with with a 1, we need to shift this 1, 2, 3 positions we have a 1 shifted number of bits minus 1 positions. So now we have this. Now we OR this with x. No, we AND this with x. And now we're left with this, or possibly all zeros. Maybe it's easier to just take the x and shift it the other direction. So here we have this bit, and we shift it 1, 2, 3. So bits minus 1, position to the right. And now we can just AND this with 1. I think this is right. Okay, so what about the other direction? That will be rotate right 1, B and X. I want to push this 1 step to the right. Which means this 1 will fall off the edge and this will be replaced by 0. Let's start there. So we take the X, shift it 1 bit position. And same as before, we OR it with something. And this time we want to grab this bit, which is to the rightmost position. Which means we can just AND it with 1. So X ANDed with 1. So now we have saved this bit. Now we need to take this and shift it 1, 2, 3 positions to the left. Which means B minus 1 positions. And we OR it with this. Lot of parentheses. I hope I got this right. How can we test this? Let's try it with an int32 first. Let's set this to, we need to do something simple. So let's say we have the number 2, which looks like this. Maybe we can start with a byte instead. So we have something like this. That's a 2. Maybe we can have a 3. So if we rotate this one step to the right, it's going to become this. And what is this? 81, I think. So x is equal to 3, y is equal to, and we rotate right 1. And we have an 8-bit thing, and we provide the x. And if I have calculated this correctly, we should have 0x80 right here. Let's see if it works. Cast to pointer. That's right. This should be a regular char. Okay, it compiled. 81, yes, that's correct. 81, yes. So if we have a 0x81 and we rotate this left 1-bit position, we should go back to the 3. And we do. Pretty nice, pretty nice. Okay, so let's create a function which does this multiple times. So let's see here how we're gonna do this. Let's say we have I suppose we need different, let's see here. We need a bunch of functions for this. So let's first say we have an int 16, and this is rotate left 16 bits, or let's see, keep doing the same. This is called 1, but this is 1 bit, so let's call this rotate left 16. And we're going to provide the input, which is an int 16 in this case, and we're going to provide how many bit positions we want to move. And this will be an int 8. Let's see here. Let's code this function first. So int 16, rotate left 16. We have an int 16 x, and we have an int 8 let's call it n for number of moves. So let's say we have an int 8I, which is equal to 0. We're going to repeat this as long as it's less than n, I++. And we need to have a variable with function scope. Let's do this. This is the input. So we have an int 16 in this case, x, which is equal to the input. Then we do this for loop where x is equal to the rotate. It doesn't fit on one line, I think, which I hoped it would do. All right. So rotate left 1. And what's the order? First, the number of bits. So these are 16 bits. And this is the x. And we repeat this n number of times. And we return x. Something like this. So between the different functions, what will change? This here will change, and this too, and this. So if we were to create a macro out of this, let's call it rotate left. And the only thing we need to provide is the number of bits, b. So let's see here. Here we're gonna have int, and we merge this with b, and we merge this with b. Same here. And here. And here. I think this is right. So now we should just be able to do, we define a function with 8 bits. and 16 and 32 and 64, 128. I think that's enough. And then we need to do the same for the right position. So this will be rotate right, rotate right, rotate right. So something like this. So we use macros to define a bunch of functions. Pretty neat, huh? Let's also use it for defining the signature. So how would a signature for this function look? Something like int followed by the number of bits, and the function name is rotate left, followed by b, and which inputs do we have? We will have int something and int 8. So something like this. And same in the other direction. All right, I think this is going to work. Ah, nice, we can see how it expands. So int 128 rotate right 128, int 128 int 8, rotate right 128, input n x is equal to input I. Okay, pretty cool. Do we need to add something here? No, I don't think we do. However, I want to have one generic version of each as well. So let's say we have a macro which is just called rotate left with one argument, which is the variable. And then we use a generic trick, provide x, and if we have an int 8, we want to call the function rotate left 8. And we want to provide the X. We do need to provide the number of positions. So this we called P. So X and P, something like this. I like these generic functions or macros. Very nifty feature. So now we have the left. Now we do one for right as well, where we only change this. Here I made a mistake. This should be rotate left 64. Rotate left 64. Rotate left 128. Right 32. Rotate right 64. Rotate right 128. All right, so let's test this then. So let's start with the 3 like before. So 0, 0, 0, 0, 0, 1, 1. And let's move this 1, 2, 3, 4. So all of these will be moved to the other side, I guess. 0, 1, 1. 0, 1, 1. And then we have these 4 zeros like before. And this 0 as well. Okay, so what is this then? I think this will be 0x 40 with this one. And what is this? That would be a 20, I guess. So I think the result would be 0x60, but I'm not entirely sure. Let's try it out. So we'll start with a 3, and we're going to rotate this left. Three positions. And this is what it expands to. All right, let's see. If this doesn't work in the first go, it will be very difficult to troubleshoot, so I hope it works. Wrote 1671. Okay, that's a nice one. This should just be an L here. This should be 16. Okay, it compiles. 0x18. 0x18. What's that in binary? So 18. What direction are we moving in? Rotate left. I meant rotate right. But let's check if rotate left worked. So we get this. So 0, 0, 0, 1, 1, 0, 0. And here we have this. So 1, 2, 3. Yeah. The left worked. Let's see if the right works. 0x60, bottom dish. And let's see what happens if we do a int 128 instead here. And how do we print one of those? Well, we do show of y. And I have no idea what this is supposed to be, but let's try it out. It should probably be a rather big number. Look at this. It's so beautiful. 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 Maybe I should make a library out of just these macros. They are pretty neat, I think. All right, so now we can rotate. After the break, we will start working on the key schedule, the G function and so forth. So we'll be right back after this. All right, you guys, welcome back. So let's keep writing these things. By the way, before we continue, I just want to fix one thing. Because we got these undefined behavior errors. I think it was the C box. Yes, it didn't. No, not the C box. The X box. So y I pointer plus plus is equal to the x of n. This probably is no problem. And here we need to increase this. So let's see here. Plus plus. So we should be able to change this. If we do this, and this, and then we need to increase it once after this as well. So it's not quite as beautiful, but it'll have to do. So something like this. And maybe we can remove that suppression of the warning. This right here. And let's see what it says. It's still complaining. High pointer equal to this. Why is that undefined? This should be rather self-explanatory, I think. idx equal to idx and plus plus idx. idx equal to x or x plus plus. No, this can't be any problem. So let's leave it like this. And you shouldn't usually remove these undefined behavior things, but in this case I am certain it's no problem. Alright, so where were we? Let's go to the generate subkeys. So we create a round key where we provide, let's see here, POX, last subkey, let's create an int64 RC. Set RC equal to the P of RCs of X. Replace this with the RC. So now we can push this through the G function, where we provide the last subkey and we provide the round constant. And how did we define G? We just have int 168. We should put this here as well. And I think this function will be rather easy to write actually. So let's see here. G function int 128 input, or let's call this K, and int 64 RC. So what are we gonna do here? Maybe it's easier if we call this X for input and we have an int 128 Y for output. And first we rotate this um, 7-bit positions to the left. And now we're gonna push it through the S box. So let's say we have a semi-word pointer. We point this to the semi-word of address of P, and if we were to move 16 bytes, we would move past it. So we want to move 15 bytes. And we want P to be equal to the S box of P. But before we do all this, we need to do the multiplication, which is just Y times RC mod, and this should be 2 to the 128. And what is that? Let's see if we have 2, 3, 4, 1, 2, 3, 4. So these are 32 bits. Maybe we can do something like this. So 32, 64, 128. Is this right? Let's move this, 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 and this. So we have 32, 64, 128. I think this is right. Integer constant is too large. Let's try it anyway. So first we do this multiplication modulus 2 to the 128. Then we do an S-box substitution of 12 bits. But since we are changing 12 bits, we need to do some additional magic. We need to, let's see here. Because we are 4 bits off. I think we need to rotate this left 4 bits, then we do this, and then we rotate it back 4 bits. No, I don't think we need to do this. This is enough. And then we return y. Easy peasy. So how do we test this one? Let's see here. Let's just give it a round constant of 1. So we see if the S-box substitution works. Okay. Wrote 1870. Rotate left 8. Rotate 18. Line 70. Huh? Maybe I mistyped it inside of here somewhere. Rotate left 8. Rotate left 8. Rotate left 8. But this worked just before. In function G, Y7. Let's start by fixing this one. Let's not do a modulus because it will just overflow anyway. So this will fix this. And then we have this semi-word problem. I guess it has to do with this. How did we do this in the Xboxes function? Okay, maybe we need to take a detour. Let's say we have a void mem, and mem is equal to the void of address of, wait a second, address of P. This should be the address of Y, right? Maybe we can just do this now. Okay. So let's figure this out then. The best way to debug these macros is usually to remove all the includes temporarily. Except this one. And then we should be able to run GP, what's it called? Is it GPP? No. CPP. XSC 256.c. So now we will see all the macros expanded. So let's see this int 8. Rotate left 8. Int 8, int 8, int 8, rotate left 8. I think everything looks rather fine. Let's check the G function. So generic int 128 y. Int 8, rotate left 8. Int 16, rotate left 16. Int 128, rotate left 128. think it looks fine. Maybe there's some limits to this generic, that it can't handle 128-bit integers, because it's trying to expand it to an 8-bit, but or maybe we just need to move this thing. So we put it under these. Could it be that easy? Huh. At least we got a different error this time. Y is used uninitialized. That might be true though, because y is equal to this of y. That's not it. It should be x right here. Okay, now it compiles. So what do we get? We get blah 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 180. So this is what has gone through the S box. 0 turning to 18, basically. But I really wanted to change over here. So maybe we shouldn't do this. Maybe we should just do this. Oh wait, we do the rotations and stuff. Let's not for now, because I want to see if this works first. Still 0. want to come over here. Why is it only changing it over here? Oh, maybe this should be minus. Weird. Whatever I do, it doesn't seem to make a difference. Okay, so that seems to work. This is really weird. So this changes this. And what happens if we increase this? Okay. Okay, so now we're over here. Maybe we need to do what I talked about before. That we rotate this to the right 4 bit positions. We do all of this, and then we rotate it back. We should rotate it left, and then rotate it right 4. Or maybe the other way around. Rotate right, rotate left. Okay, so now we get the 5 here at least. But we don't want the 5. We want the S box of star P. Why does it become 0? Okay, we don't have a show function for semi-words. We should most definitely have that. So show 128, show int. something like this, and then we have char input.x y and z. And let's add this to our list. So my word. Oh, show semi-word. And where did we put our g function? Here. So let's see, sbox of semi-word 005 is 0. Why is that? Oh, wait a second. Did we not create the sboxes? No, we didn't. That's why. So we've been troubleshooting this all along just because I didn't call the make sbox function. So let's call that inside of our main. So make sbox. Okay, that's better. So now we get this instead, which is perfect. Perfect. And what if we add the rotation? So we change this to y. All right. And let's change this right here to star p instead. Star p. Oh. So sbox of star p is 0. That is probably true, because if the input is 0, we are currently making the output 0. And I don't really like that. If we go to make it, we're gonna create better S boxes later on, but for now, let's do this manual. So S box of 0, 0, 0 should not be 0. It should be anything but. So let's say 555 or something. Okay, that's better. Okie dokes. Pretty nice. Maybe we can change this to star P. Do we get the same thing if we do this? Yes, we do. Very nice. So what are we doing here? We are rotating left 7. Then we are changing the most significant 12 bits through the S box. And we do the multiplication. But currently we're multiplying by 1, since we get this 1 here. But let's say we do P of 0xAABB instead. What will the result be? Okay, now we're talking. So one round changes it to this, which means that if we push this through all the 15 rounds, we will have quite nice keys. Alright, so now I have the G function. If we go to generate subkeys, okay, looks right. So let's try this function. So let's say we have an x which is 3 from the beginning. That's our encryption key. And then we want a round key structure. A round key is equal to generate subkeys. And all we provide is our input key, which is x. And then we can show our key and see what we get. Oh, let's remove this S box thingy. So int 128G. This shouldn't be here, though it looks nice. So the first subkey is just 3. The RC is 1. I want to see the rest of the subkeys. So we go in with the key 3. After one round, we have this, and then this, then this, and it keeps changing quite a bit, which is exactly what we want. And the last one, everything has changed. Very nice, but let's print the RC in a better way. So show round key, LLD, let's make this 0x dot 16x. Okay, that looks better. So the first RC is just 1. The next is 1, 1, 1, 1, like this. And then we have 2, 2, 2, etc. And this is what we multiply the key with. So now we have successfully created a key schedule, ladies and gentlemen. And we have created all the internal functions for the encryption. The only function we have left, basically, well, there are 2 actually. Let's see, we have a state type. So what we're gonna have is we're gonna have a function that we're going to export, which is one part of our public API. So this is going to be public, and we're going to create something which returns an int 8. And let's call this the XSC 256 byte. And it's going to take a state star, and that's it. And in order to be able to code this function, we also need to have a round function. And the round function is probably going to return void and just take a state as input, because the only thing it's going to modify is the internal state, which contains the list of subkeys and the 16 bytes of state. And the round function will just call different of our utility functions. Basically, it's just going to fill in all of the bytes in the new state by calling the f function and some rotations. But this is enough for one day. I hope you liked this episode and that you will continue watching this series and subscribe because next time we're gonna finish this thing. So thanks for watching. Thanks for today.